Need it. All right, all right. Starting in just a minute.
I'll tell you the last one. And I said the biggest one was like 0. Yeah.
All right. Come on in, have a seat. Hopefully everybody had a nice long weekend, got to relax a little bit. Now the final push, 2 more weeks, then finals. Got a few things to cover. Let's see, today is what, the 28th? Sure. Matrices and all that jazz. Before matrices, we should say a few more things about vectors. So let's back up just a minute here. Yeah, let's go ahead and do that. So we started last time to talk briefly about projections. We should kind of finish that discussion and then we'll talk about matrices, which really have to do a lot with vectors. So just as an example, to remind everybody what's going on, if you've got 2 vectors like A equal to, I don't know, 3, 4, and B equal to 1, 5, the way you find the dot product, the easy way of finding the dot product is you just multiply the components together and add the result. So A dotted with B is just going to be 3 times 1 plus 4 times 5, which is 3 plus 20, which is 23. And this is true for vectors of any size, meaning if you have a vector with 3 components or more, which do exist, you can do the same sort of thing. So for example, if you had 2 other vectors like v equal to 1, 2, 4, 3, a 4-dimensional vector, which we don't really deal with in this class, but still is not impossible. And w equal to 3, 0, -1, 5. You can find their dot product in the exact same way by just doing v dot w equal to 1 times 3 plus 2 times 0 plus 4 times -1 plus 3 times 5. And you get something, what, 3 minus 4 plus 15 is going to be 14. The dot product can be extended to sort of vectors of any size, which is totally fine, which also then means we can find other things like magnitude and angle between things. So if you want to find, this is kind of just a reminder of what's going on last week, the magnitude of the vector A. Ooh, here's a way you can calculate it. Instead of doing, well, it's really the same. You could think of it as the usual thing, the square root of 3 squared plus 4 squared, which is just the square root of 25. But I would like everyone to notice that you could also calculate this as the square root of A dotted with itself. So if you take the dot product of a vector with itself, you actually get the square of its length or the square of its magnitude. So if we square both sides of this equation here, you look at the magnitude of A squared, that's equal to just A dotted with itself, and vice versa. And that comes up occasionally. But we could also then think of the length of a vector in more dimensions. So if I said, what's the magnitude of V? Well, we could say that's going to be the square root of 1 squared plus 2 squared plus 4 squared plus 3 squared, which is something. Square root of 1 plus 4 plus 16 plus 9, which is the square root of 30. We could also find the angle between 2 vectors. This is a calculation that relies on our knowledge of both ways of calculating the dot product of 2 vectors. So we already know how to calculate A dot B up here. We know that from above, A dotted with B is equal to 23. But also, A dotted with B can be calculated as the magnitude of A times the magnitude of B times cosine of theta. What it should really say is, that's how it's defined. This is just the nicer way of calculating it. We can use this definition of how the dot product is calculated to then actually find the angle between the 2 vectors. So you can say, okay, well, A dot B is 23. We just did the magnitude of A was 5. We still need to calculate the magnitude of B. The magnitude of B is going to be the square root of 1 squared plus 5 squared, which is the square root of 26. Multiplied by cosine of the angle between the 2 vectors. So if we want to find the angle, first we find cosine of the angle. We say cosine of theta is equal to 23 divided by 5 times the square root of 26. And then to find the angle, you have to use a calculator. Well, I should say you don't have to use a calculator. You can write that the angle is just the inverse cosine of 23 over 5 root 26. Or if you prefer, and I do prefer the notation, the arc cosine of 23 over 5 root 26. Just some angle that I haven't calculated. I have one in my terrible phone calculator with me. Awful, it's the worst. Well, let's see what it is just for the fun of it. So we do use the sideways phone calculator, even more terrible. Is there even an inverse cosine function on this? Oh, I don't know if there is. Might be out of luck here. I don't think we get to know it. Sorry. Someone wants to calculate it, they can, but again, not really that important. If you can get to here, that's what we get. Oh yeah, okay. I know it does. Yeah, okay. Good to know. I should have known that. If you press second, oh, do I have a second? Oh, there we go. Yeah, there we go. So, oof, all right. So we've got 23 divided by 5 divided by the square root of 26. All right, that seems not at all right.
I think you do.
I got it now. I'm good. And then the arc cosine of that is okay, 0.44. Oh, but I'm in radians. Terrible. I don't want it in radians and I have to switch to degrees. I can just change that to, let's see, times 180 divided by pi. Okay, so we're getting approximately 25 degrees. Sure. Don't use your phone calculator. If you have to actually calculate this, use a regular normal calculator. The phone calculator is terrible for doing stuff like this. So please, please, please do yourself a favor. I should do myself a favor and actually bring my calculator to class. So then the other thing we're going to talk about briefly is projections. So there's kind of two things to talk about with projections. And we talked about the first part of it last time, which is that if you want to find the projection of A onto B, which we write as the projection of A. I always write the A part first onto B. The B is the subscript there. The way we're going to calculate that is as follows. We're going to draw it. There's our vector A, there's our vector B. And what you're always thinking about doing when you're projecting a vector onto another vector is dropping a perpendicular from the vector you're projecting onto the other vector you're projecting onto. So that vector that I'm drawing there, that vector, okay, that is the projection of A onto B. It is a vector. And really, I think of it as just the amount of the vector A that is in the direction of the vector B. And if you have something that looks more like this, where A and B, or where I should say, where the angle between A and B is greater than 90 degrees, then you get a projection that's going kind of in the opposite direction. So the scalar component here will be a negative, and this will be your projection of A onto B. The good news is you don't really need to know this picture or have this picture to find the projection. It's probably something you want to memorize, as the many things in this class. The way I usually think about it is I'm thinking of this angle as the angle between the two vectors. And I'm just going to find the length of the projection, which we call the component. So the magnitude of the projection of A onto B is equal to the component of A onto B. And the way we're going to find that is by using cosine. So cosine of that angle is the adjacent over the hypotenuse. That is the component divided by the magnitude of A. I'm going to do this slightly differently than I did it last time to show you a little bit different way of doing it. Last time I multiplied both sides by the magnitude of A and magnitude of B because I knew I wanted the dot product to show up on the left-hand side. I'm essentially going to do the same thing this time, just a little bit different. So first I'm going to multiply both sides by the magnitude of A and get the magnitude of A times cosine theta equal to, that looks gross there, the component of A onto B. Quick reminder here, the reason I'm doing this is because when I see cosine theta, I'm dealing with vectors, I know I should try to make the dot product appear. That's really the driving force here is, oh, I see a cosine, try to make it so the side with the cosine looks like the calculation of the dot product. So then I'm also going to multiply this side. Now here's where I'm going to do things a little bit differently. Instead of multiplying both sides by the magnitude of B, I'm going to multiply this left side by the magnitude of B divided by the magnitude of B. Totally legit, right? It's multiplied by 1. But then the top here, that's the dot product of A and B. So I can say that the length of the projection, the component of A onto B, is equal to the dot product of A and B divided by the magnitude of B. And I think that's about where we stopped last class. So this is how long that vector is. So this vector here has this length, and that is a numerical value, right? A dot B always just gives you a number. The magnitude of B also just gives you a number. To get the vector, we're going to do is we're going to take the length of the vector and multiply it by the direction of the vector. But when someone says direction of the vector, they specifically mean the vector that points in the same direction that has a length of 1. Has to have a length of 1, so that when you multiply it by 17, you get a vector of length 17 pointing in the right direction. So that's how you always get a vector of the length you want, in the direction you want. You take the vector in the direction you want it, you make it a unit vector, and then you multiply that unit vector that's in the right direction by the actual length you want your vector to be. So here, to get the projection of A onto B, it's going to be this length of the vector we want, A dot B divided by the magnitude of B, times the unit vector in the direction of B. Whenever you want to make a vector into a unit vector in the same direction, you take your vector and you divide it by its own length or its own magnitude. The drawing on the right isn't valid, correct? The drawing on the right is totally valid. You can have an angle bigger than 90 degrees for sure. It's totally valid. What will end up happening in this case, if your picture looks like this, is this part here will end up being a negative value because the dot product always ends up being negative if the angle between the two vectors is larger than 90 degrees. But it's a totally valid picture. Normally this calculation gets rewritten a little bit. There's two equally good. There are two ways people write it. I think one of them is better. Shocking, I know. I would write it, well, I wouldn't. People write it as A dot B divided by the magnitude of B squared all times the vector B. Or I prefer A dot B divided by B dot B times the vector B. Either way is correct. They're both the same. Yeah, well, so I would say, so someone asked, we would still use the same formula, but it'll come out negative. I'd say you're still gonna use the same formula. It's not that it's gonna come out negative, it's just that you're gonna end up multiplying B by a negative value. So the vector is gonna point in the opposite direction. That's what's gonna happen. Yeah.
Can you explain how you got from the component of A over B to projection of A over B?
Sure. So I took the component and I multiplied it by the vector that's in the direction of B, but that's a unit vector. So I took B and divided it by its own magnitude. So that I'm taking essentially, so actually, let's look at an example real quick. So let's say our vector, let's use the two vectors we had from before. The vector, what is it, 3, 4, and 1, 5? Yeah. Let's say, yeah, we'll try this. We can draw this. So here's the vector 3, 4, 1, 2, 3, 1, 2, 3, 4. I don't like 1, 5. I'm going to change it to 5, 1. So here's A, just because this is the direction I find it easiest to draw a projection in. And here's B. And they're almost the same length, but they're not quite the same length, right? B is a little bit longer, not that it really matters. So we're going to find this projection right here. So first, let's find the component of A onto B. So again, A is the vector 3, 4. B is the vector 5, 1. So the component of A onto B, just not working through the calculations, just going to the straight kind of answer, is going to be A dotted with B divided by the magnitude of B. I should have chosen the other way. Oh, well. That's going to be A dot B. Let's see. So 3 times 5 plus 4 times 1 divided by the magnitude of B, which is the square root of 5 squared plus 1 squared. That's going to be 15 plus 4, so 19 divided by the square root of 26. So around 4-ish, a little less than 4. So what we're saying is this new vector that we're finding has a length of approximately 4, a little bit less than 4, whatever. But that's just how long it is. We want the vector that actually points in the same direction as B. So to get the projection, we're going to take the length of the vector that we want. We want this length. And we're going to multiply that length by the unit vector in the same direction as B. That's going to be the vector 5, 1 divided by the magnitude of B, which is, again, the square root of 26. So when we multiply this together, the denominator actually becomes a little nicer because you get the magnitude of B squared. So we end up getting 19 over 26 times 26 times the vector 5, 1. And if it were up to me, I would leave it that way. But you could also distribute the 1926 if you really, really wanted to and get something terrible like 95 over 26, comma 19 over 26. If you wanted to write the vector that way. I would not. I mean, I don't think you need to is the more important thing. I think you can leave it like that and everyone's happy with that. So here's what we've ended up with. 1926 is clearly a fraction that's less than 1. And I think you can see from my picture that, oh yeah, this new vector that's the projection of A onto B should be a vector that's less big than the vector B, right? It's some smaller than 1 fraction of the vector that it's pointing in the same direction as. So that's the whole calculation, is you're taking the component here and multiplying it by the B divided by the magnitude. Now, if we only have to find the projection, we often end up skipping writing it out this way. So for example, if I wanted to go the other way and find the projection of B onto A, and nobody asked me to find the component as an intermediate step, I would jump straight to saying, okay, well, it's going to be B dot A over A dot A times the vector A. That's the final calculation I would just skip to. So in this case, B dot A is going to be, again, 3 times 5 plus 4 times 1. It doesn't matter what order you dot product two vectors in. Still going to be the same result. I guess I could say it's going to be 5 times 3 plus 1 times 4 if you want to be very order specific about it. Divided by the magnitude of A, which is the square root of 3 squared. Oh, sorry. No, I said the magnitude, but I meant to say the dot product of A with itself. But I'm just going to write it as the magnitude squared because it's the same thing. A dotted with A is the magnitude of A squared. And then we're going to multiply that scalar by the actual vector A, which is the vector 3, 4. So this ends up being what? Again, 19 on top, 19 divided by 5 on the bottom. Sorry, not 5. 5 squared, 25, times the vector 3, 4. So if we're projecting, yeah, I can make that work. If we're projecting B onto A, it's going to look like, and I'm dropping a perpendicular from B to A. It's going to look like that vector there. There's the projection of B onto A. A vector that points in the same direction as A, but is again a little bit less than A because of the vectors I've happened to pick here. A projection doesn't always have to be less than the vector it's projecting onto. Just the ones I've chosen here look like they are. But not just look like they are. Why does the square root cancel? Because I have a square root of 26 times the square root of 26. And the square root of 26 times the square root of 26 is the square root of 26 squared, which is 26. Yeah. So you only need to use the component if someone's asking you to, right? Like I was trying to show the longer calculation, but if someone said just find the projection, then you could just use this calculation and be done with it. But if someone wanted you to find the component and the projection, then you might as well kind of do it in this intermediate way. What does the component mean? The component is exactly how long the projection is or the magnitude of the projection. So it's kind of, we often think about vectors as a completely being described by a direction and a length. So when we think of it that way, it's nice to kind of split it up into writing it this way, where you literally have the, write it this way, you have the length and the direction. Just leaving it written this way is very unsimplified and unsatisfying, so we do more to make it look nicer. Yeah. Sure, that's fine. Oh, yeah, question.
So you were saying that it would be squared, right? And then it became 25 because you're not.
Well, because let's actually calculate it. 3 squared plus 4 squared is 9 plus 16, which is 25. The square root of 25 is 5, but then 5 squared is 25.
And then that's when you would use, like, it would be squared instead of when you solve for the component.
Right, so if I had done this the longer way, I could have done this as the component of B onto A multiplied by the direction, which would have been just the B dot A over the magnitude of A multiplied by A over the magnitude of A. And then that would have been, well, B dot A is still 19. The magnitude of A is the square root of 25, which is 5. And then it'll be multiplied by the unit vector in the direction of A, which is the vector 3, 4 divided by 5. So that's a way of thinking, oh, there's the length of your projection. There's the direction of your projection, which is just the direction of A. How did we get square root 26 under vector B? Because the magnitude of B is the square root of 26, right? If you take the square root of 5 squared plus 1 squared, 5 squared is 25, 1 squared is 1, 25 plus 1 is 26. Let's do one more example because it's one other thing we should mention here. Sure. Yeah, let's do one more thing, point in a different direction just to kind of have some fun. So let's say we have 2 new vectors. Sure, I'm going to make them kind of easy. Let's say that U is equal to the vector. Yeah, sure. 12, 5, and V is equal to the vector 12, 5. Let's see. Don't want to go more that way. All right, sure. Negative 4, 3. I'm picking vectors that have nice magnitudes, just so in case you weren't aware. So here's what we kind of look like here. Over 12, up 5 might be like that. Here's the vector U. And the vector V is left 4, up 3. Maybe looking somewhat like that. Again, these are approximations. They're not perfect. And let's say we want to find, sure, the projection of U onto V. It's going to look kind of funny. I mean, can I even draw it here? Maybe. Yeah. So I think my picture is going to be kind of wild here because if I tried to extend this out here, right, I'm trying to actually need to extend it this way so that I can drop a perpendicular from U onto V or onto the line that V is in. So right here, there's my projection of U onto V. Oh, yeah. Huh. Let me see one thing here. Yeah, I like that. All right. So let's find the component first. Actually, let's not. Let's do the actual calculation first, and then we'll go back and find the component. So if I'm just finding the projection of U onto V, here's what I think about when I do this really. Like if I'm trying to remember the formula, I remember it's a bunch of dot products. There's 2 things on top, 2 things on the bottom, and then you multiply by something. And the thing you're projecting onto the other thing, like the thing that's getting projected, only shows up once. So if I'm projecting U onto V, I'm going to get 1 U and the rest are V's. So it's 1 U, U dot V, the rest are V's. V dot V and a multiply by V. That's actually how I remember it. I think it's fairly convenient. So then it's going to be, let's see, U dot V is going to be 12 times negative 4 plus 5 times 3. V dot V, I'm going to actually do it this way, is negative 4 times negative 4 plus 3 times 3, and then multiply by the vector negative 4, 3. Let's see what we get. So we get negative 48 plus 15 divided by 16 plus 9 times that. That's going to be, let's see, negative 33 over 25 times the vector negative 4, 3. So we're ending up with a vector that's longer than V, right? Because 33 over 25 is a fraction larger than 1, but it's pointing in the opposite direction of v, which is why we have a negative there. I would leave it like that, right? There's no value to doing anything else here. If you wanted to find just the component of u in the direction of v is going to be just the dot product, u dot v, divided by just the magnitude of v. So that's going to be u dot v is still negative 33. The magnitude of v is the square root of 16 plus 9, which is the square root of 25. That's going to be a negative 33 over 5. So the length of that vector is negative 33 fifths. I misspoke there. The length of that vector is positive 33 fifths. But we say the component is negative 33 fifths because it's the component of u in the v direction, and v is pointing in the opposite direction. So we do need that negative sign there. At least I'm pretty confident we need that negative sign there. As far as my notes say, yeah. Yeah, exactly. Assigned magnitude. One last thing, which I don't know if you talked about in class, but sometimes it's asked about, is this vector here. The projection, or sorry, not the projection, the orthogonal complement. So the orthogonal complement of u onto v is really easy to find if you find the projection. Because look here, the projection plus the orthogonal complement is equal to the vector. So it's always going to be the case that the orthogonal complement of u onto v plus the projection of u onto v is equal to the vector u. So if you know the projection, you know the vector u, finding the orthogonal complement is just a subtraction problem. The projection, yes, the complement and the question, the complement and the projection are different things. Yes, they are. The projection is the actual vector. The component is just the length of that vector. It's like the difference between the vector and its magnitude.
Would you be able to use Pythagorean theorem?
Well, you can find you can use the Pythagorean theorem to find the length of that vector, but we're trying to find the actual vector. So it's actually, I think it's actually easier than using the Pythagorean theorem. We're just going to subtract vectors. So if I want to find the orthogonal complement here, it's going to be equal to the vector u minus the projection of u onto v, which in this case is going to be the vector u, which is 12, 5, minus the vector that's the orthogonal, the projection, which is this vector here. So here we might actually need to do a little bit of doing. So minus negative 33 over 25 times the vector negative 4, 3. I would probably make this minus a plus, because why not? So I have 12, 5 plus, I guess we need to do, yeah, 33 times 4 is 100 and something, 132 over 25, and 33 times 3 is 99, but it's a negative it's a negative 132 over 25 and a positive 99 over 25. And then you get a common denominator and put things together, so that's going to be 12 times 25 is 300 over 25, comma 5 times 25 is 125 over 25, plus negative 132 over 25, comma 99 over 25. And I guess we might as well finish it since we're almost there. 300 minus 132 is 268. And 125 plus 99 is 224 over 25. So there's your terrible looking orthogonal complement. Again, the calculation part, not the most important part here. The most important part here is knowing that you find it by doing your vector minus the projection. And really the picture is what's helping me do that. If I think about drawing the vector u and drawing the projection, then the orthogonal complement is just the difference between the two. All right, so moving along. Yeah, those are fine. Matrices. was a lot more fun to talk about matrices when the movie The Matrix came out, but that was a long time ago, but not that long ago. Anyway, so what's a matrix? It's a list of numbers written in a grouping of rows and columns. We often think about the rows and columns as vectors. So not that we have to think about them that way, but if I say that the matrix A is the matrix 2, 1, -3, 5, I often think of it as having a row vector of 2, 1, and -3, 5, and column vectors that are 2, -3, and 1, 5. We don't have to use those words, but sometimes people will. Here's a matrix B. It's also a 2 by 2 matrix, 4, 0, 1, 3. And here's a matrix C. It's a 2 by 3 matrix, 6, 1, 2, -1, 0, 1. So this is, we don't typically label matrices with their dimensions, but we will for the moment. This is 2 by 3. This is 2 by 2. This is 2 by 2. The first number refers to the number of rows. The second number refers to the number of columns. So number of rows, number of columns. So a couple things we can do with matrices. We can add them, we can subtract them, we can multiply them by a scalar. But there's some rules. So adding, subtracting. We can certainly add A and B. A plus B. And fortunately, kind of like with vectors, actually a lot like with vectors, matrix addition and subtraction works how you would imagine it would work. You're going to add the like component, the corresponding components together. So the result here, if I want to add A plus B, in the first row, first column, I'm going to get 2 plus 4. In the first row, second column, 1 plus 0. Second row, first column, -3 plus 1. Second row, second column, 5 plus 3. I would encourage you to skip writing this if you're comfortable with it and just write and just do the addition and get 6, 1, -2, 8. Not too terrible. We can also relatively easily multiply a matrix by a scalar or a constant. Meaning if I looked at, say, 3a minus 2b, before I do the subtraction, I'm going to do the multiplication. So I'm going to have 3 times the matrix A minus 2 times the matrix B. And when you have a matrix multiplied by a scalar, you just multiply each component of that matrix by that scalar. You have a couple options here. The 3 I'm going to distribute through and get 6, 3, -9, 15. Over here, you could either write it as minus all these components times 2 or plus all these components times -2. Either way is fine. I would probably write it as minus all of them getting multiplied by 2. So 8, 0, 2, 6. And then we subtract the matrices together in the same way you would add them together. 6 minus 8 is -2. 3 minus 0 is 3. -9 minus 2 is -11. 15 minus 6 is 9. On the other hand, if matrices are not the same dimension, size, what's the right word here? Yeah, dimension. I probably use either word actually. The matrices have different dimensions. You cannot add them together. So for example, A plus C is undefined. We cannot add A to C because you run out of parts of A when you still have parts of B to add to it. Just generally, if you have questions, feel free to ask them. I know you are, but like, just want to make sure that, like, if I'm not addressing something, that just don't hesitate to ask. That's pretty much all there is as far as adding, subtracting matrices together. It's, again, relatively straightforward. Let's talk about multiplying matrices together. So multiplying matrices. And we'll still use the same matrices we just had. So let's look at A times B. That's going to be the matrix A, which was 2, 1, negative 3, 5. By the way, when someone reads a matrix to you, they will typically read it as all the things in the first row, and then all the things in the second row, and so on and so on. I guess people could do it differently, but I've never really heard anyone do it differently. So I would read this as 4, 0, 1, 3. So when you multiply two matrices together, we take the rows of the first matrix and we dot them with the columns of the second matrix in order. And this is something that actually took me a while to learn, is that not that part, but the part that whatever row you're using and column you're using, you're going to end up with that entry in your resulting product. Meaning, when I use the first row of A dotted with the first column of B, I'm going to get the entry that's in the first row and first column of my product matrix. So A dot with B, that's going to be 2 times 4 plus 1 times 1. This row with this column. And typically, the way we continue on here is that we keep using the first row of A until we've exhausted all of the columns of B. So now I'm going to use the first row of A dotted with the second column of B, and I'm going to get the entry that's in the first row and second column. So I'm going to get 2 times 0 plus 1 times 3. Now I've done everything I can with the first row of A and the columns of B, so now I move down to the second row of A. Now it's the second row of A dotted with the first column of B. That's going to be negative 3 times 4 plus 5 times 1. And no surprise, that's going to end up in the second row and first column of my result. Finally, the second row, second column, negative 3 times 0 plus 5 times 3. To me, this is why we have spent time talking about the dot product, because when you multiply matrices together, you're always dotting rows of the first matrix or left matrix with columns of the second matrix or right matrix. That is always, always, always how we do it. There are, I think, other ways of actually multiplying matrices together, but you shouldn't explore them. This is the best way. Don't do it a different way if there is a different way. So then we simplify. We get 8 plus 1. We get 0 plus 3. We get negative 12 plus 5. We get 0 plus 15. So there is the product A times B. So there's a question here. So when subtracting or adding matrices, they have to be the same. They have to be the same. Yes, like a 3 by 2 minus a 3 by 2. You can't do a 3 by 2 minus a 2 by 3. That's exactly correct. They have to have the same exact number of rows and columns to be able to add or subtract matrices together. Which is not true for multiplication. They don't have to have the same number of rows and columns. They do have to have something being the same. So let's look at a matrix multiplication that's not going to work. Let's look at, for example, C times A. So if we try to write out C times A, here's what's going to happen. We're going to have the matrix C, which is 6, 1, 2, negative 1, 0, 1, multiplied by the matrix A, which was the matrix 2, 1, negative 3, 5. And the problem here is that the number of columns of C, or how long the row is in C, doesn't match how long the column is in A, or how many rows there are in A. If I try to do the dot product of this row with this column, it doesn't work. 6 times 2 plus 1 times negative 3 plus 2 times I've ran out of things. So this is not defined. And the thing we look for to see if a matrix multiplication is going to work or not is that when you look at these two matrices, this matrix is a 2 by 3 matrix. This matrix is a 2 by 2 matrix. If the inner dimensions, the 3 there and the first 2 there, if those don't match, then you don't get to multiply. If they don't match, then the multiplication is not defined. So another way of saying this is the number of columns in your first matrix has to match the number of rows in your second matrix. But really, you can just look at it. It's like if you write it out and look at it, you're like, okay, yeah, if I tried to do that with that, not going to work. So So someone asked if we had C times, well, C times A times B, I think is totally fine. I don't think you have to think about moving around. So let's look at C times A. Oh, no, sorry. No, sorry. I back it up. So there is no way to move it around to make it defined. So if you had C times A times B, which is a 2 by 3 by a 2 by 2 by a 2 by 2, the A times B is totally fine, but A times B is going to be a 2 by 2 matrix. The 2 by 3 is still not going to be able to multiply that. So typically, once it's undefined in some way, there's no rearranging to make it defined. Yeah.
That little triple works if it's the bigger one on the front.
Nope, you can have it. Well, you can have, when you say bigger, what do you mean, I guess?
Like, if you flip them,
Mhm.
the 2 would be on the inside and then the
Right. But it really, I could have like, as long as the inner dimensions match, it doesn't actually matter what the outer dimensions are. So you could have something like a 5 by 2 multiplied by a 2 by 7, but you could also have a 2 by 5 multiplied by a 5 by 3, right? So as long as the inner ones match, it doesn't matter if they're bigger or smaller. So let's actually do it the other way. So let's calculate both A times C. If you want to do A times C, that's going to be this 2, 1, negative 3, 5 multiplied by 6, 1, 2, negative 1, 0, 1. Same process as before. We're doing rows of the first matrix dotted with columns of the second matrix. So I'm going to do the following. Yeah, that's enough room. So 2 times 6 plus 1 times negative 1. There's my first row, first column. First or second column is going to be 2 times 1 plus 1 times 0. First row, third column, 2 times 2 plus 1 times 1. And then I'm going to, now I've exhausted the first row with all the columns of the second matrix. So now I move down to the next row. So this row, that column, so negative 3 times 6 plus 5 times negative 1. And then negative 3 times 1 plus 5 times 0. And then negative 3 times 2 plus 5 times 1. Again, I think you can skip writing all that out. And I think you should skip writing all that out once you feel comfortable. And just say, yeah, I'm going to get, see, 12 minus 1 is 11. 2 plus 0 is 2. 4 plus 1 is 5. Negative 18 minus 5 is negative 23. Negative 3 plus 0 is negative 3. And negative 6 plus 5 is negative 1. Also of interest or of note is that when you multiply two matrices together, the inner dimensions have to match, and the outer dimensions are the dimension of your resulting product. So here, the inner dimensions match. We have a 2 by 2 multiplied by a 2 by 3, and the outer dimensions are the dimensions of your resulting product. And that is also always true. Right, exactly. We couldn't do C times A, but we could do C times A. Or sorry, we couldn't do C times A, but we could do A times C. Apologies. Something else. Oh, yeah, that's the other thing I want to say. So something that's important about matrix multiplication, which is not true about other multiplications you have probably encountered in your lifetime, mostly just multiplying numbers together, is that order matters. So in regular numbers, 3 times 7 is equal to 7 times 3. They're both 21. But we calculated A times B before. I'll remind you it was 9, 3, negative 7, 15. Let's calculate B times A and see what happens. B times A is going to be the matrix 4, 0, 1, 3 multiplied by 2, 1, negative 3, 5. If we multiply these together, we get this row with this column. So I'm not going to show the intermediate step here. I'm just going to multiply it out. So watch how here's how I'm doing this. I'm just pointing, I'm saying I'm getting 8 plus 0. And then first row, second column, I'm getting 4 plus 0. And then second row, first column, 2 minus 9. And then second row, second column, 1 plus 15. There's my resulting product. And look, that is for sure not the same as A times B. There's A times B up there. There's B times A down there. So it is generally true that when you multiply matrices in the opposite order, you do not get the same result. Yeah. It doesn't matter. But so really the answer is you should do whatever you want. For me, I would probably do the matrix multiplication first and then multiply the 3 in afterwards. In fact, and let's look at an example of a similar kind of thing. So A times B does not equal B times A. What we say is the matrix multiplication is not commutative. I should write that down. So matrix multiplication is not commutative. So definitely when you're multiplying matrices together, you have to keep them in the order they are written in. You cannot just move them around like at will. But let's say we want to do one other thing, and let me make sure I've got this the right way here. Sure, I don't want that. Right. Let's say I want to find. Sure. Let's give ourselves some new matrices. I'm tired of these matrices. Let's have some new ones. So let's say we have A equal to, here's my favorite 2 by 3 matrix, 1, 2, 3, 4, 5, 6. Very easy. Say B is equal to this 2, 1, 0, 5, 8, 3. And what else do I want? Sure, let's make it terrible. C is going to be 1, 4, 3, 2. So let's say we want to find, yeah, all right. Sure. C times A times B. First of all, does it even exist? Let's see. So C is a 2 by 2. A is a 2 by 3. And B is a 3 by 2. Yeah, it's going to work out. All the inner dimensions match. The 2's match here. The 3's match here. It's going to work out. And the resulting matrix is going to be a 2 by 2 matrix. So now the question is, what do we do first? Well, the answer is it doesn't matter. You can either do the C times the A first or the A times the B first. You just have to pick. And really, I mean, it's probably going to be, you're not going to avoid any awfulness by doing one thing first and something else second. You're going to either get it, you're going to get the more awful part at some point in the process. So it really doesn't matter which way you pick doing this. So let's do C times A first. So I've got 1, that's a 1, sure, that's a 1. 1, 4, 3, 2 times 1, 2, 3, 4, 5, 6 times 2, 1, 0, 5, 8, 3. And we're going to just look at doing the first 2 matrices multiplied together first. This is an example of what's called an associative property, meaning when you have 3 things multiplied together, you can pick any 2 to multiply together first. And technically, you have done this a lot with regular numbers. Like if I said, you know, what's 3 times 5 times 10, pick whichever 2 you want first. You can either do 3 times 5 times 10, or you could do 3 times 5 times 10. Right? You're not actually multiplying all 3 of them together at once. It's just so it's relatively easy enough for us to do that we kind of feel like we are. But really, just like with matrix multiplication, regular multiplication is what's called a binary operation, meaning you're taking 2 inputs and getting 1 output when you multiply things together. The same thing is true here. It's just a little bit more rigorous. All right, the fun part of multiplying them together actually. So let's see. So here we go. So when I do this, I should be getting a 2 by 3 matrix. 1 times 1, 4 dotted with 1, 4. I really should stress. Remind yourself that when you're multiplying these matrices together, you are dotting the rows with the columns. So we're going to get 1, 4 dotted with 1, 4 is going to be 1 plus 16, so 17. And then this with that is going to be 2 plus 20. I do think the pointing really actually helps me. Like when I do this, I really like to point at like the first row, third column. I'm going to get a 1 times 3 plus a 4 times 6. That's a 3 plus a 24. So 27. And then a 3 plus an 8. That's an 11. A 6 plus a 10 is going to be 16. A 9 plus 18 is 27. Oof, okay. Dotted with this other. So now I'm going to have to be more careful because my numbers are getting kind of big. Oh, all right. It's going to be kind of gross. let's see what we're gonna get here. So I have a 2 by 3 multiplied by a 3 by 2, so I should get a 2 by 2 matrix at the end. So 17 times 2 plus 22 times 0 plus 27 times 8 is not my favorite. 2 times 17 is 34. 0 times 22 is 0. 8 times 27 is, thank you. And then this row, this column, so 17 plus 22 times 5 is 110. 27 times 3 is 81. And then second row, first column, isn't 27 supposed to be 21? Good question. Which 27? This one here? Let's see. Let's double check here. 9 plus 12. Yeah, 21. Good call. Thank you. I'm glad we got there before I got there. So then second row, first column is 22 plus 0 plus 8 times 21 is 168. So 22 plus 168. And then second row, second column, 11 plus 80 plus 63. And then whatever that is. I mean, I guess we could write it out. We're almost there. 250, 191, 208, 190, something else, 154. Sometimes the numbers get a little bit gross. But that's the nuts and bolts of matrix multiplication. It's always rows of your first matrix with columns of your second matrix. And I don't think there's a lot more to say about matrix multiplication specifically. But I should pause. Questions about matrix multiplication at all? The good news is in 17C, you're only ever really going to be multiplying 2 by 2 matrices by 2 by 1 matrices. So they're not going to get too gross. There's other things we're going to do with matrices, but which are also not that bad. But as far as the size of the matrices you're dealing with, you're really dealing with 2 by 2s and 2 by 1s, which is not that bad. A couple other things that we do with matrices, though, is we talk about the transpose. So let's look at this matrix C. Let's say C is equal to, sure, 1, 0, 5, 3, negative 4, 2. Transpose is kind of the easiest matrix thing you've ever seen, I think. The transpose, which we write as either C with a superscript T or sometimes with a prime, although I do not like the prime notation. But I'll say for C prime. People do write it that way, but you shouldn't. C transpose is equal to, it's literally just the columns become rows and the rows become columns. So this first row becomes the first column. This second row becomes the second column. Or if you want to use different words that give you the same thing, this first column becomes the first row, the second column becomes the second row, this third column becomes the third row. That's it. That's all there is to a transpose. The kind of fun thing about transpose matrices is you can always multiply a matrix by its own transpose. So if you want to find, say, C multiplied by C transpose, it'll always work. If I do that, it's going to be 1, 0, 5, 3, negative 4, 2 times 1, 3, 0, negative 4, 5, 2. I'm going to get 1 plus 0 plus 25. 3 plus 0 plus 10. 3 plus 0 plus 10. 9 plus 16 plus 4. 9 plus 16 plus 4, 29. And the resulting matrix has a special property. It's symmetric. What does it mean to be symmetric? It means this matrix here, let's call it D. It is its own transpose. So it's symmetric, meaning D and D transpose are the same. I don't know if they've talked about symmetry, but it felt like I should say it because it was a ripe moment to say it. It also works if we multiply them in the other order. So if you multiply C transpose by C, the matrix multiplication will also work. We're going to get a different result though. Because again, when you multiply matrices in the opposite order, with rare exception, you get different results. Very, very rarely you get the same result, even though you've changed the order of multiplication. Here, if we multiply it the other way, it's going to be a bigger matrix. So 1, 3, 0, negative 4, 5, 2, multiplied by 1, 0, 5, 3, negative 4, 2. All right, let's see what we get here. So 1 times 1 plus 3 times 3 is 10. 1 times 0 plus 3 times negative 4 is negative 12. 1 times 5 plus 3 times 2 is 11. 0 times 1 plus negative 3 times 4 is negative 12. 0 times 0 plus negative 4 times negative 4 is 16. 0 times 5 plus negative 4 times 2 is negative 8. 5 times 1 plus 2 times 3 is 11. 5 times 0 plus negative 2 times 4, sorry, 2 times negative 4 is negative 8. And 5 times 5 plus 2 times 2 is 29. This matrix is also symmetric. I will just point out, if you took the transpose of this matrix, it would still be the same. Cool. Oh, there was something that occurred to me. We'll come back to that. Sure. Matrix multiplication all day long. Oh yeah, we should talk about that. Okay. There are some special matrices. Ooh, yeah, there are some really special matrices actually. So a few matrices that I think are important. Let's talk about them for a second. So first of all, not just I think these are important. These are important for you in the future, possibly also in this class. First of all, square matrices. So square matrices have the same number of rows and columns. So 2 by 2, 3 by 3, 4 by 4, etc. Any matrix where the number of rows and columns are the same is a square matrix. So for example, A equal to 1, 2, 3, 4 is square. And there's some special square matrices that I want to mention, specifically the following ones. So first, you can have an upper triangular matrix. An upper triangular matrix is a square matrix. Oh, I forgot one. That's all right. Is a square matrix where everything below the main diagonal is 0. So here's an example. Here's two examples. This matrix, 1, 2, 0, 5, and this matrix, not 0, 9, 3, 4, 0, 1, 7, 0, 0, 6. So I should point out this right here is the main diagonal of the matrix. It starts at the upper left corner, it ends at the lower right corner. You only talk about the main diagonal for a square matrix. And if your matrix is upper triangular, it means everything on or above the main diagonal can be non-zero, but it doesn't have to be. But everything below the main diagonal is 0. We love these matrices in 17C. They're the best. We won't talk about why just yet, but trust me, you're gonna want to see upper or lower triangular matrices. So in a similar way, a lower triangular matrix, I bet you all could write out 2 examples of what a lower triangular matrix would be. In fact, why don't you try writing out a 2 by 2 and a 3 by 3 example of a lower triangular matrix? If you're having trouble seeing something, please don't hesitate to ask.
What's the word before diagonal?
Main diagonal. I would not, so someone asks, this would mean they're symmetric as well. So being symmetric is not synonymous with being square. Square just means the number of rows and columns are the same. Symmetric specifically means that the matrix is equal to its own transpose. So if I call this first square matrix, if I call that A for a second, A transpose is not the same as A. A transpose would be the matrix 1, 0, 2, 5, and that is not the same as A. So this upper triangular matrix here is not a symmetric matrix. I will point out its transpose is a lower triangular matrix. So here are some lower triangular matrices. Here's my lower triangular matrix C. Let's call it 3, 0, 5, 7. It is okay to have zeros on the other side as well. So I don't like to write them that way, but for example, here's a 3 by 3 lower triangular matrix. Everything above the main diagonal has to be 0. Everything below or on the main diagonal is a free-for-all. Be anything you want. I like them to be non-zero just to kind of show the difference. But you could have zeros everywhere if you really wanted to. So 1, 2, 3, 0, 5, 7. Here is another lower triangular matrix. And yes, you can have a 0 there, that's fine. Yeah.
So the diagonal have to go from like top left to bottom right?
Yes, it does. That is always the main diagonal. Sometimes, specifically with the 2 by 2, I call this the main diagonal and the other two the off diagonal, but that language doesn't really apply to larger matrices. Yeah, I don't know why we don't just call it the diagonal as opposed to the main diagonal, but I suppose you could talk about like the once removed off diagonal, like either above or below, but yeah, the main diagonal is the only one we really care about. Next quarter, I believe, we'll talk about adding up the components of the main diagonal. So like if I said, if I added 1 plus 5 here, I would get 6, and we would call that the trace of the matrix. I don't think that's something we talk about so much here, but it is something that does come up next quarter. It's not hard to calculate, right? The trace of a matrix is easy. You're just adding up the entries on the main diagonal. Let's see. Oh yeah. So, but the specialist of all matrices that I want to talk about is the identity matrix. Well, I should say identity matrices. Really, there's a number of them. There's one for each size. Oh, you can't see what I'm writing. Identity matrix or matrices. So here they are in all their glory. I2, the 2 by 2 identity matrix, is this matrix here, 1, 0, 0, 1. I3, 1, 0, 0, 0, 1, 0, 0, 0, 1. And I bet you could guess the rest of them from this point on. I'll write one more. I4, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So identity matrices are super special. They are a class of diagonal matrix. A diagonal matrix is specifically a matrix that is both upper and lower triangular, meaning everything not on the main diagonal is 0. But these are all diagonal matrices. And just as another example, here's another example of a diagonal matrix, D equal to 1, 0, 0, 0, 2, 0, 0, 0, 5 is also a diagonal matrix. And I'll say it one more time. It just means everything not on the main diagonal is 0. Everything on the main diagonal can be whatever you want it to be. You could have a 0 on the main diagonal, but I don't in this case, but you could. What's special about the identity matrices? They're like the number 1 in that if you multiply a matrix by them, it doesn't change them. So the number 1 is what we call the multiplicative identity in the real numbers. If you multiply any number by 1, you get that number back. 1 times 5, 5. 1 times -7, -7. Just like we call 0 the additive identity. If you add 0 to any number, you get that number back. 0 plus 7 is 7. 0 plus -3 is -3. In the same sort of way, we have a multiplicative and actually an additive, but we have a multiplicative identity for matrices. These right here. If you take, say, for example, I times the matrix A, I'm just going to make up an A right now. So take the matrix A like 1, 0, 0, 1 times the matrix 1, 2, 3, 4. you exactly get back the matrix you started with. 1, let's see, 1 times 1 plus 0 times 3 is 1. 1 times 2 plus 0 times 4 is 2. 0 times 1 plus 1 times 3, 3. 0 times 2 plus 1 times 4, 4. And somewhat uniquely, the order you multiply the identity matrix on doesn't actually matter. So if I multiply it the other way, if I said A times I would get 1, 2, 3, 4 times 1, 0, 0, 1, and I would still get the same result back. 1 times 1 is 1. Sorry, 1 plus 0 is 1. 1 times 0 plus 2 times 1 is 2. 3 times 1 plus 0 times 4 is 3. And 3 times 0 plus 1 times 4 is 4. Yeah.
Does it only work if A is the same size?
Well, no, it doesn't. For example, but I will say, with the commutativity, the being able to multiply in the opposite order only does work if A is a square matrix. But A doesn't have to be square to be able to be multiplied by an identity matrix. For example, if we have my favorite 2 by 3 matrix, 1, 2, 3, 4, 5, 6, which I know is not exciting, you can multiply this by an identity matrix and still get the same matrix back, but you have to make sure it's the right size. So for example, A times I3, the 3 by 3 identity matrix, which is going to be 1, 2, 3, 4, 5, 6, multiplied by 1, 0, 0, 0, 1, 0, 0, 0, 1. That'll work out to be just A. And you can check, right? This dotted with that's going to be 1. This with that's going to be 2. So on 3, 4, 5, 6. But if you want to do the matrix multiplication in the opposite order, you would need a different size identity matrix. You need I2. So I2 times A is 1, 0, 0, 1 times 1, 2, 3, 4, 5, 6. And you exactly get the same result. 1, 2, 3, 4, 5, 6. But there's no commutativity here because things aren't the same. It is also worth mentioning that, is it worth mentioning? Maybe not. I was going to say, diagonal matrices will commute with square matrices. So for example, just as an interesting point, the diagonal matrix D, let's say it's equal to, sure, 2, 0, 0, 5. If you multiply D by, so if A is any 2 by 2 matrix, then it is true that D times A will equal A times D. And this is a special property of diagonal matrices, where everything not on the diagonal is 0. Let's actually look. Why not? Let's take a look real quick here. So let's say my D is 2, 0, 0, 5. And let's say that A is, let's pick something different than what you usually pick, James. 3, 1, 2, 5. Sure, that should be fine. I mean, it shouldn't matter what I pick. It should work out. Let's see what we get. 2 times 3 plus 0 times 2 is 6. 2 times 1 plus 0 times 5 is 10. 0 times 3 plus 5 times 2 is 10. 0 times 1 plus 5 times 5 is 25. Let's go the other way. I hope I've not said something really stupid. I don't think I have. 3 times 2 plus 1 times 0 is 6. 3 times 0 plus 1 times 5. Ooh. Uh-oh. Uh-oh. Did I make a mistake? I might have made a mistake. I might have said something crazy. Oh, maybe I'm wrong.
I think the 10 in the upper right-hand corner
Should it be? Let's see. Yeah, but but either way, I think I'm wrong. I think I've said something that is totally inaccurate. I apologize. I'm gonna have to, sorry. Ignore the last few words I said. Don't pay attention to that at all. I'm gonna have to go think about that. Sorry, I really thought I was saying something that was true. I apologize because I've diagonal matrices. Oh, 6, 2, yep, but that definitely does not come out the same. 6, 5, yeah. Huh. Maybe it's only, you know what it might be? Maybe. Yeah. Yeah, okay, yeah. I think it just multiples of identity matrices. I am so sorry. I did not mean to present false information to you. That is the lie. I told you lies. Terrible. Okay, let's see, what time is it? 5 minutes left. Is there anything else I can say to absolve myself of that terribleness here? No, but I mean, we should talk about that for 1 second, though. So here is something that actually is true, not just pretend, really is true. It is true that A times B transpose is equal to B transpose times A transpose, which is kind of funky. That when you multiply two things together and transpose them, it comes up being that you're transposing them first, but multiplying them in the opposite order. And let's look at this very generally. So sometimes, especially in the doubles class, you might be asked to kind of show something is true for any like, let's show this is true for 2x2 matrices. But here's the deal. If you're asked to do this, you can't just pick, like I've been doing, a matrix like 1, 2, 3, 4, another matrix like 5, 6, 7, 8, and then do it both ways. That shows it's true one time, but maybe you just picked a special example. So if I want to show this is actually true for any 2x2 matrices, what we're going to do is we're going to say, well, let's say that A is, there's two ways I pick general matrices. You can either say A is A, B, C, D, or you can use, if they get big enough, you start using subscripts, but let's not do that. And let's say that B is the matrix E, F, G, H. And now we're going to calculate both things both ways. So let's do the left-hand side first. So A times B transpose. We're just going to multiply the matrices together. So it's going to be A, B, C, D times E, F, G, H. And at the end of the multiplication, we're going to transpose it. So let's see, usual thing, A times E plus B times G. And then A times F plus B times H. C times E plus D times G. So it's important to make sure you write your letters clearly. C times F plus D times H. Transpose. And then to transpose, you just change rows in the columns and columns in the rows. So this is going to end up being, so AE plus BG, that's a G, right? That's a G. And then you're going to have CE plus DG. And then my bottom row is going to be AF plus BH and CF plus DH. Now let's calculate the right-hand side. So right-hand side. So B transpose, A transpose. Well, luckily, transposing them first is actually pretty easy. So B transpose times A transpose is going to be, B transpose is E, G, F, H. A transpose is A, C, B, D. And then you multiply those together and we get, I'm still going to write it in the right order. So I'm going to E times A plus G times B, but I'm going to write it as A times E plus B times G. And then E times C plus G times D. So CE plus DG. And then F times A plus H times B. So AF plus BH. And then F times C plus H times D. So CF plus DH. And look, they're the same. So that's kind of how you would show something, like if someone asks you to show something is true for any 2x2 matrices, you make them very general. You don't pick actual numbers. You're like, oh, here's some 2x2 matrices. Multiply them together. Last thing I want to say, I know I got less than a minute, but you're probably going to start talking about inverse matrices next, but specifically only for 2x2s, which are actually not that bad. So I just want to point out that for the matrix A equal to A, B, C, D, the inverse of A, written as A to the -1 power, which is A, but you should read it as A inverse, is going to be 1 divided by the number AD minus BC, which we'll talk about later, multiplied by the matrix where you interchange the diagonals, and the off diagonals you change the sign of. And you should check on your own when you have a minute. that A multiplied by A inverse is going to give you the identity matrix. Which is the whole point. When you multiply a number by its multiplicative inverse, what do you get? Right, the multiplicative identity. We're just making a matrix inverse instead of a numerical inverse. But that's the whole idea. It's just like with regular inverses, when you multiply them by their inverse, you get the number 1. When you multiply a matrix by its inverse, if it exists, then you get the matrix equivalent of the number 1, which is the matrix identity. I should mention, this quantity doesn't always exist, because sometimes that denominator there, AD minus BC, sometimes that's equal to 0. And I will just, I will finally say one last thing. The determinant of the matrix A is equal to the quantity A times D minus B times C for a 2x2 matrix. For larger matrices, it's a more complicated process of calculating the determinant. But for a 2x2 matrix, it's always the product of the diagonals minus the product of the off diagonals. And that is a calculation you're going to use a lot next quarter. So you should definitely get it ingrained right now. The determinant of a 2x2 matrix, you multiply those together, you subtract multiplying those together. All right, I should stop talking. Apologies for the error before. I'm going to go think about that a lot. I'll see you all later. I really thought that was true. Yeah, of course.
Okay, so I have 2 quick questions.
Yeah.
So I was looking back at your videos.
Uh-huh.
And then, okay, so when it came to solving this problem, right?
Uh-huh.
Okay, how did you get this? Like, I don't know, like, I tried to look at it like multiple times, I'm not.
Well, so basically I said I have -1 equal to -1 divided by something, right? So if I have, let me ask you a different question.
Okay.
If I have like 2 equal to 2 divided by A plus B, what does A plus B have to be?
2, right?
2 divided by 2 is what?
Oh, 1.
Right, it has to be 1, because I know that 2 divided by 1 is the only way I'm gonna get 2.
Oh.
So I'm just saying, oh, I know that 2, I mean, I can also write it this way, 2 divided by 1 equals 2 divided by.
To equal each other.
Right, but I was just taking a shortcut really. But I was saying, oh, if these are equal, that has to equal that. There is no other choice.
Okay, good. I get that.
Good.
Okay, and then I have one more.
Sure. I should stop and zoom here.